So this is the example that we're going to work on. And we're going to start with an example in this little, I don't know, weird elbow fitting, okay? So we have flow coming in the wide part of here. We force it to turn the corner and go out through this narrow part. Why? I don't know. It's a problem. So the question is this, right? If we have this situation and we have 0.4 cubic meters per second flowing through it, what's it going to take to hold this fitting in place, right? And that's a smart question to ask, because this elbow, you're not changing the mass rate of water flowing through there, right? Flow in has to equal flow out. You're changing its direction, so you're changing the little hat on the V, and you're changing its velocity, because it's going from flow through a big wide tube to flow through a narrow tube, right? Which means you are changing its momentum. So if we change the momentum of the water, it's going to generate a force. And so the question is, okay, it's going to generate a force. It's going to push, right? How hard do you have to be able to push back against it? Or how are you going to hold this thing into place? If I wanted to put my hand around this thing and hold it in place, how much force am I going to have to apply? And in which direction? Is this fitting going to try to blow off this way, and I need to have something there to hold it or support it? Or is this fitting going to try to crush the pipes that way? Either way, it's a problem. It's exerting a force, and that's going to slowly wear out the system. Right? Every time you change the velocity of water, this thing's going to jerk in one direction or the other. Okay? We'll do some open channel problems as well, where we look at dams and gates and how we have to anchor stuff in place. But this in a pipe is one of the easier versions of this. So we're going to ask what's the magnitude and what's the direction of the horizontal force to hold this thing in place, and then what's the magnitude and direction of the vertical force to hold this thing in place. So it might also be trying to either push up or push down. So just like we did in hydrostatics, we're going to break this into two components, an X component and a Y component. All right, so that's the setup. Horizontal. So our momentum problem says the sum of the forces in the X direction should equal the mass rate flowing through this thing times the velocity out minus the velocity in. That was the equation we starred and smiley faced, and we're so happy to have a simple looking thing, right? Okay, so step one, we are going to draw a control volume. So we are going to somewhat arbitrarily choose what we want to analyze here, okay? So that we can split up the forces that are acting on it, which is the left-hand side, from what's going through it, the right-hand side. So just as we did for conservation of mass, we want our flows to be perpendicular to our control surface, right? So where these things say section 1 and section 2, I'm going to draw my control volume right along those, and it doesn't really matter what else I do with it. So we'll just kind of loop around. Okay, so now ideally here we want to think about a free body diagram for this thing, okay? And so I'm going to just doodle our control surface down here again so I can cleanly draw on it. So we're interested now in X-directed forces, horizontal forces, right? what horizontal forces are acting on this thing? So Heather says influx of water, so you're pointing at this part, right? You're saying there's water moving in. So the water moving in is part of the right-hand side. No, it's okay.
So it's holding up from the outside,
So,
assuming it's not, it's fixed.
yeah, so we've sort of invoked this idea that there must be some resultant force holding it in place, right? That's actually what we're after. So we need to manifest that in the problem. So that's one force. So Ross, let's say we took, I don't know why I'm picking on Ross, he caught my eye.
Gravity.
Gravity, yes, but in the vertical, we're not on that slide yet. But good, but you're out of the hot seat for a moment, you contributed. So imagine that we have this pipe of water flowing across the top. This horizontal pipe is flowing, okay? And we just took we took this away. We took away our fitting, right, at this control volume, right? What would happen?
Free jet.
You'd have a free jet here, right? But this is not a free jet. This is still compressed. So there is some pressure inside of this pipe, right? If I put a wall here, if this was an open jet and I put my hand over it, it would try to push my hand away, right? So there is a force, there is a pressure force being exerted right there. This is a pressurized pipe. This doesn't have pressure 0, right? If it was a free jet squirting into here, it would have no pressure, right? Pressure 0 in a free jet. But this is a pipe. Flow inside that pipe does have a pressure, right? We don't know what it is, but we could imagine that, you know, on this, if we picture this round surface right here, there is a pressure multiplied by an area that does generate a force. And similarly, down here at the bottom, there is a pressure multiplied by an area. Now, this is a spot where people get grumpy, because you'll notice this second one that I drew, this pressure times area at the outlet here, I drew it pushing in on the control surface, right? And your heart says, Adam, man, water is flowing the other way, right? Shouldn't the arrow go the other way? But then you remember hydrostatics. Pressure is equal in all directions, and we're asking about forces that are acting on the control volume right now. Right? What are the forces that are acting on the control volume? Not forces that are inside the control volume pushing out. What is the world doing to the control volume? And so just like there's pressure in the horizontal pipe, there's also pressure in this diagonal pipe. And that pressure is acting equally in all directions, which means it's also pushing on the control surface.
I'm more grumpy that we're analyzing X and you drew it at an angle.
Well, that's troublesome as well, right? So if we're going to think about the X-directed components and the Y-directed components, then we get to do some trigonometry too.
Well, didn't you just say it's omnidirectional? So why then do we have to take components?
So it is acting because pressure forces act perpendicular to the surface.
Okay.
Right, so think back in hydrostatics, we always took pressure as perpendicular to the surface. No matter how that surface was oriented, it's perpendicular to the surface.
Okay.
And then if you want the X component, you have to do some trigonometry. So all of this to say, the left-hand side of this equation is going to look like, I'm going to put a minus fx. Why minus? Because I'm picking that positive in the x direction is to the right and negative is to the left. I will always pick positive to the right and negative to the left. Just like I'll always pick positive is up and negative is down. Like years of math class have drilled into me that's how axes should work. So we have minus this f of x. So that's the first one that we drew. The second one, I'm going to deal with this horizontal force. So it's in the positive direction, and it's whatever the pressure is at the inlet times the area of the inlet. And then I'm going to deal with this last one that we got a little grumpy about. That's in the positive direction. I'm going to have a pressure at the outlet, area at the outlet, and I'm going to have this trigonometry cosine of 45 degrees because I want the horizontal component of it. Are folks seeing where those came from? And we're making sure, because these are forces, we have to think about those directions, right? So I made a point of reminding myself that these minuses and pluses go with each of those terms. That's giving us the directionality. So all of this that we just drew, or just wrote out, that's the left-hand side of the equation. That's the forces. Then the right-hand side, for the right-hand side, we have our mass rate multiplied by these velocities, right? Now we don't know our mass rate in this problem. We do have a Q, so we could write it as density times discharge times, so we'd have our velocity out minus our velocity in, right? So for velocity out, we don't actually have, if you look on the previous slide, you don't actually have any velocities given to you in this problem. But you do have Q's and you do have A's, right?
Why is it density and not specific weight?
Oh, did I screw up?
Well, here on the equation sheet you have rho, but on the previous slide you wrote gamma.
Ah, so I screwed up.
Somewhere.
So on the...
Gamma, because...
No, so because gamma would be a force. So that's all right. So, all right. Bottom left-hand side of the slide in purple, mass rate is a density times a Q, or a density times an area times a velocity. On the previous slide, I had drawn in green pen with a specific weight.
So when you said watch out, you
When I said watch out, I meant
Watch out for me.
don't make the mistakes I make. Yes. Yeah, sorry. Good catch. Yes, and it's density, and we know it's density because it's a mass rate, so we want a mass per unit volume. If we were using specific weight, it would yield a weight rate, which is not what we want. Weight rate is how I think about myself at Thanksgiving. Like, how many pounds per day of turkey am I eating? I want slugs per day. I want mass. Thank you for catching that. Sorry about that, guys. I am infinitely fallible. Okay, so let's take our velocity out term, right? So V out. It needs a magnitude and it needs a direction, right? So its magnitude is not bad. Its magnitude is Q over A out. And I'm getting that because we have our Q equals area times velocity, right? So that came from Q equals AV, which I just wrote in green down along the bottom also. So that's the magnitude of velocity out. Now what about its direction? So let me ask first, is velocity out in the positive or negative direction?
they're both?
So a little bit of both.
Oh, sorry, no.
So,
Never
all
mind.
right.
Not-
So it's
yeah, along
in
X is
general,
negative.
the x directed part is moving to the left. So it's broadly in the negative direction, right? So I'm gonna make sure then that I put, and I'll do this in red, I guess. I need to make sure I get a negative sign in there.
Minus cosine hat.
So let me just redraw it with the negative sign to be super explicit. So negative for the direction we just looked at. Q over A for the actual magnitude. Now, Josie, tell me what you just said again.
Well, since it's at an angle, if we're going perpendicular to the outlet, it's not perfectly along the axis.
So some of that velocity is directed in the x direction, but not all of it.
Mm-hmm.
So the stuff that is going in the x direction, we need a cosine 45 degrees to make sure that we get just the x component of that velocity. So everything we just did here, that stuff is our v out. Yeah?
So when we're in the x component, we don't worry about the y component of the velocity.
Yep.
Okay.
Yep. When we're working in x, we are blind to other directions. We're always just wanting the components in the direction we're working. Okay, so that's velocity out. Now, the equation tells me to put a minus sign here. There's the minus that we don't mess with. Always a minus. Now, what about our velocity in? So, I'm drawing this blue arrow up here to help us think about velocity in. What direction? Is it positive or negative? Positive. I've heard a couple whispers. So it's positive. Magnitude Q over A in. And that's A in, right? Which is a different area. And over here in black, I should have written A out in the denominator. Right, that first term should be Q over A out. This should be Q over A in, the area of the inlet. And do we need any trigonometry on there? So that's all in the x direction, so we're going to keep all of its magnitude, right? So this stuff plus Q over A in, that's our V in. Woofta. Okay. Do folks see where this came from? It's tricky, right? That we have to jump back again to drawing free body diagrams. And in a free body diagram, we're thinking about how the world is acting on our control surface, right? What are the forces at the control surface? That's the exact same mental leap that I asked you to make when we did forces on curved surfaces. We drew that volume and we said, okay, is there pressure pushing on it from the left? Is there pressure pushing down on it from above? You did this, right? You drew a volume and you analyzed stuff acting on the surface. And it always was pushing on the surface. It was never about how what's inside is pushing out. It was always about what's pushing on the control surface. So we had to think that way to get the left-hand side. And then for the right-hand side, we had to very carefully think about directionality. So that's plus or minus and cosine or sine or tangent, right? So there's the directionality piece, which has a plus or minus and potentially trig, and a magnitude piece, which is, in this case, we did Q over A for that velocity. So it's ugly, but we could find all of these things. And they're all things that we've actually done quite a lot of in this class, right? Pressure, force is pressure times area. We've done this. Q equals AV, we've done this. Components, we've done this. We've never stacked it all together this way before, but we've seen all these building blocks. Okay, so sparing you me plugging in numbers, which is actually all that remains. You have Q's, you have diameters, so you could get these areas. You have densities, you have pressures, if we go through and do the math, this Fx comes out to be about 25,700 newtons. So by forcing this amount of water to go through this fitting, you are generating this force, about 26,000 newtons. And because it comes out as positive, it means we got the direction right. So it is 26,000 newtons in this direction that you have to hold on to this with. So you cannot just make water change directions without getting punched back by it. Right? You make water do something, you gotta earn it. You want it to turn the corner, you better put something there to hold it in place, because it generates serious force when you make fluid turn corners like this. Excuse me. Okay. Does this idea make sense? Folks feel okay about this version? That's horizontal. Whew. Vertical. Aye. So, vertical. I'll get us started in that I'm going to draw the exact same control volume I just used. Sum of the forces in the y direction, mass rate, V out minus V in. So there's our momentum equation, just like we've had. All right, so, and I'll draw our little idealized one down here so we can goof around with it. All right. What do we have for forces in the y direction? I'm going to draw, I'll start us. I'm going to write, the book usually writes these as FR, comma x and FR, comma y. And what they're meaning is it's a reaction force. Like this is the force to react to or offset what you make the fluid do. So I'm sorry I didn't do that on the previous slide. So I'm going to guess that there's a vertical force that we're going to lift up on this thing. I actually don't know if that's the direction it is, but got to make a guess. Okay. Y-directed forces that we need to think about. What other forces do we have? Ross calls dibs on gravity. Yep. So there is, I'm going to draw FW, weight, meaning. And there is potentially two weights at play here. So one, you have a fitting that actually weighs something. You must have made this out of, I don't know, metal or plastic or whatever. It's not magically weightless, right? So we should at least consider that it might have to be held up. And it's full of a fluid, and fluids are heavy. So there is also a weight of fluid in there potentially. Okay? What else?
Yeah, pressures.
We got pressure forces, right? So we've got pressure in, area in, and here we had pressure out, area out. Yeah? So, the left-hand side of this equation, I've got my vertical reaction force in the positive direction. I would have minus those weight forces in the negative direction. Now what about the inlet? Is there a vertical force at the inlet here? No, that's perfectly horizontal, right? So at the inlet, we don't need to deal with a pressure force. What about at the outlet? Okay, in the positive or negative direction? Positive, because there's a component in this diagonal force down here in blue, there's a vertical component that would push upward, right? So plus P out, A out, and again, sticking our trigonometry on there to get the correct.
Could be sine this time, wouldn't it? They're technically equal.
Yes, yeah, for probably for correctness, we should write sine there, not cosine. So there's our left-hand side. Our right-hand side then, mass rate, again, I'm going to write it as density times Q. So that's my mass rate. All right, V out. Is that in the positive or negative direction in terms of Y? Negative, right? So it's coming out, so there's the vertical component is directed down. So minus Q over A out. And again, we're going to throw the sine of 45 degrees on there to do the trigonometry, just to get the vertical component. What about velocity at the inlet? Is there a y-directed velocity at the inlet? Everything at the inlet in this case is perfectly horizontal, right? So we could write minus 0, I suppose, if we wanted to be complete in our notes, just to remind ourselves that that's a 0. And the careful reader of the problem will note that I told you in the givens to ignore the weight. Not every problem will, but if you're not able to ignore the weight of the fluid, then this thing better be simple enough that you could calculate its volume and calculate a weight force, right? So if you're not given information, or if you don't think you have enough information to know what is the volume of water inside this thing, or the volume of oil or whatever fluid you're dealing with, if you don't know the volume, it's probably a good assumption that the weight forces are going to be negligible, or that you're going to ignore them. So in this case, we have no prayer of knowing what is the volume of this thing. If the problem setup said the volume of the fitting is 1.2 liters, then you would have a prayer of calculating the weight of fluid. You'd take the volume times the specific weight. But in this case, I explicitly told you to ignore it on the 2 slides ago and however many equations ago, and we all read it very quickly. Okay, folks, see where these numbers came from. Or where these terms came from. Gonna take silence as a yes, I guess. Okay, some nods, that's reassuring. So again, math magic, and I got this y-directed force of about 3,520 newtons. And because it comes out as a positive number, it means that the way I guessed was correct. If this would have come out as like minus 4,000 newtons, what that would tell you is the magnitude is 4,000 newtons, and the direction is the negative would basically mean you made your guess wrong. It would be that your arrow should have faced the other way.
How are you getting a positive? You're adding 2 negative numbers on one side of the equation. I don't understand how you're getting a positive number. To get our bar y, you have to subtract over the pressure term, and so you're subtracting more from your flow rate.
Did I screw this up? Tell me I screwed this up, huh? So you think that...
Suggesting there might be an error.
Y out.
Wasn't our fx was so much bigger than our fy?
Yeah. Agreed. Yeah, but remember you have a bunch of x-directed momentum coming in, where you don't have y-directed momentum coming in. So, but I think I agree that I screwed up the negative signs on here. Is that true? All right. In this moment, I feel 90% confident that I agree that I botched the signs. All right. So let us believe that this should have been minus 3,520 newtons. And what that would mean is that I guessed the wrong direction. So I made the assumption that this was in the positive direction. when I drew it this way. Right? I drew this black y-directed force pointing upward, and I kept a positive sign in front of it when I put it in the equation. If it trickles through and you get a negative answer, what that means is you got the direction wrong. So the magnitude is correct, 3,520 newtons, but it should be in the downward direction. So this fitting is going to try to kick up, and we're actually going to have to push down on it. Just like a downward pointing fire hose creates an upward force that lifts an idiot in the air.
I'm getting 5,600 newtons.
Enough with you. All right. What I'm hearing is I need to double check my math. That is what I am hearing. Okay. Nonetheless, the key point here is setting up of these problems, not my apparent inability to have done math late last night. Okay, how do we feel about this?
I'm slightly still mildly confused that it's apparent if you get a negative or positive, I did it wrong. I'm not, am I finding the force I need to exert on the thing? Or am I finding the force that the thing is going to do?
So you're finding the force, what we've solved for here is this like, how would we have to hold it in place force?
Okay.
So I guessed that you would have to hold it up. I made the guess initially that this reaction force in the y direction would be up, which means the thing is trying to push down and I'm going to push back on it to hold it up. Okay? So I assumed that this was going to be in the positive direction.
Okay.
We went through all the math of it, and what comes out is a negative number. What this means, and the way that I want you to think about this, just like we did with the velocities, right? This plus or minus sign is the direction, and this number is the magnitude. So when you get a positive number, it tells you you guessed the correct direction. You guessed it was upward force, it turned out to be. When you get a negative number, it tells you you guessed the wrong direction. You assumed it was going to be in the positive y direction, Adam, and you were wrong. It's actually, you would have to push down on this thing. Good. Yeah, well, no problem. My botched doing this turns out to be a learning opportunity for all of us, so that's good. Okay. So what I want to start us on for the last bit of class here then